I want to talk about thoughts that we've been having over the last 2 to 3 years now about how we can improve the fault management of Lustre. First of all, I'm going to be talking about why we need this, and then the second half of the talk, I'm going to be describing some ideas for implementing fault management for Lustre. So let's start off with Elnet. Get my dirty laundry out in the open. So fault detection in Elnet is based on the LND timeout. So the low-level driver that communicates with peers on the network, it has to do some sort of fault detection so that communications don't back up to dead peers. And it uses a timeout for that. Now that timeout is completely orthogonal to any timeouts in Lustre above it. And so an immediate issue there is that if Lustre starts injecting communications into Elnet too quickly, token buildup can occur. What do I mean by that? I mean that message queues can become very long because they're all blocked waiting for a low-level network driver timeout. So that's an issue that needs to be addressed. The other thing is that just using this timeout, which is based on whether messages are moving to a peer or not, it can be confused by congestion. So in the case of a congested network, particularly with routers, what we can find is that all resources in the peer are consumed, and therefore, although everything's healthy, we're not actually moving messages into the peer. What that means is that the low-level LND timeout has to be quite long so that it's not confused by this congestion. So that's a piece of low-level infrastructure that needs to be rethought. In the layers above, I just want to go through a little bit of history about how Lustre peer health detection actually developed. So in the beginning, the only way of detecting whether a peer was in trouble was by noticing that RPCs were timing out. And actually, that's still true today. But what happened in initial Lustre implementations was that when a client died, discovery of client death was delayed until it was determined that the client was blocking some other client. So typically, the client would be holding some extent locks on a file. Another client would want to do some conflicting operation in the same extent of the file, at which point a notification is sent to the first client. That client's dead. The notification times out. The first client obtains its lock, does an I/O, progresses to the next stripe, at which point the whole story repeats. So what was happening there was that the first client, which had died, it had obtained extent locks over all the stripes of the file, and now the time to clean up after this dead client was the RPC timeout times the number of stripes. That was an unacceptable situation. And so the pinger was introduced. So the function of the pinger really was just to send keep alives, so that if we had a dead client holding down resources on servers, then eventually the pinger pings would time out. The servers, all the servers involved, would see that the client was dead. Resources would be released, and now we would no longer have cascading timeouts. So, what's the issue with pinging? Well, here's a little Lustre network. 2 clients, 2 servers. There are my pings going backwards and forwards. Everything's good. Not too many. Let's double the size of that. So now we see a few more pings going on. Still not too many. Let's double the size of that. Now we've got quite a few pings going on. Okay, now let's increase that up to 20,000 clients and a few hundred servers. How are the servers ever going to get... How are the servers ever going to get some work done? So the issue here you can see is that the fan out from any individual server is order number of clients. So if we keep the ping interval constant, then the ping overhead on each individual server increases linearly. So at some point, we have to back off from our ping rates in order to keep the overhead per server constant if we want to preserve server efficiency. So just to reprise a minute, the fault detection model, in fact, a lot of the architecture of Lustre is based around every man for himself. And the reason is that doing collectives, having some notion of the gestalt, if you like, of the whole server cluster in a distributed environment where individual servers and clients can be coming and going, it's a really hard problem. And you can actually get a long way just by ignoring that problem and saying, okay, I'm just going to deal with point-to-point issues. But at some point, the scalability issues get you. So because you're doing this every man for himself concept, we have this order n squared issue. And you can compromise by reducing the ping interval as you grow the size of the system. And what that means is that you have to basically increase your RPC timeout. So we're still in a situation where we exclusively rely on in-band RPC timeouts to do pure health detection. Now, in the large systems, network and service latency can be highly variable because it depends on load and usage patterns. So you all, or administrators here, will all be familiar of cases where clients all start converging on a single server. Now, whether that's because the application was written that way, whether it's because screw-ups in setting default striping made everything start striping at OST 0, for whatever reason, it's in the nature of distributed systems like Lustre that you can have non-scalable behavior, which leads to order n latency issues when you're talking to any individual server. Now, what that means when you've put all of your eggs into the timing out RPCs basket is that to distinguish a dead versus a congested server, you have to have really long timeouts. Now, adaptive timeouts were introduced as a way to get around this problem. Unfortunately, they don't. They don't get around the problem. What adaptive timeouts do for you is that in the case of a lightly loaded server, they will detect server failure more quickly. But in the case of a heavily loaded server, and you might assume that heavy load is the time when a server is going to belly up, you have to allow for maximum timeouts, order n on machine size. So what that means altogether is that when you're exclusively relying on in-band RPC timeouts and pingers like this, you have an order n fault detection latency. So double the size of the machine is going to take you twice as long to discover a failure. And unfortunately, the multiplier on the order n is really large. The place this really gets you is in server recovery. So Lustre is very keen to allow RPCs which change server state to happen in memory on the server so that a disk latency isn't involved. This means that, for example, we can do shared operations between different clients with much lower latency than competing file systems. And benchmarks have shown that when you do, for example, metadata operations in a shared directory between different clients, you can see the performance improvement. Now, to get that performance improvement, we have to leave dirty data in the server cache. If the server bellies up before that cache is flushed, we need to do recovery. So what recovery is basically starting up the server, taking the state that was on disk at the time the server crashed, and reconstructing the state that was in the server's memory just before it crashed. And this is done by replaying transactions on the clients. So when Lustre clients perform an update, they retain the RPC until they get confirmation that the RPC has been committed on the server. That's what transaction replay is all about. Now, in order to perform transaction replay safely, you have to wait for all the clients to be ready. You have to allow all of the clients to connect to the server and participate in replay so that you can replay the transactions in the correct order. So when you have dependent transactions, for instance, one transaction that creates a directory, the next transaction that creates a file in that directory, then you ensure that the transactions are executed in the same order during replay. Now, you can avoid the need for that by using commit on share. Unfortunately, commit on share penalizes the very operations that are Lustre's unique selling point: faster shared update operations. The other reason that you need to keep the replay window open is that you cannot allow new transactions to start executing before clients have had a chance to replay all their old transactions. If that was the case, the new transactions could invalidate the replay transactions. So it means you must give clients a chance to reconnect and participate in recovery. Now, when the only way that you have of notifying clients that they must reconnect to a restarted or a failed over server is the RPC timeout, then the recovery window has to be very long. So here's an example scenario. Let's say I'm doing file per process, 4 strikes per file. I've got 20,000 clients, 12 processes per client. That's a lot of processes. I've got 8 1 megabyte RPCs in flight. I've got 100 OSS nodes. Let's say OSS bandwidth is 2.5 roughly gigabytes per second. That gives you a rough number of RPCs in flight of 75,000. And the latency of each individual I/O is going to be on the order of 30 seconds. So to have a safe RPC timeout, to have a good margin for error so that you don't have false evictions, the fundamental timeout is going to have to be on the order of 300 seconds. And because during recovery we have to give clients a chance to work out which of the failover servers they need to reconnect to, you're now talking about a recovery window in the order of thousands of seconds. That's unacceptably long. Another issue with every man for himself is that we have no concept of global client eviction. This is a real problem for features that would greatly benefit Lustre. For example, create on write allows you to use a single file identifier, FID, for all of the stripe objects of a Lustre file. What this means is that you can compress the file layout representation to be quite small. And that means you can do very, very wide file striping. However, you must provide a guarantee somehow with create on write that a client doesn't attempt to access a stripe object and therefore create it after the file itself was destroyed. That will just create orphans. Similarly, for caching attributes on the metadata server, whether it's for caching the size to make ls-l go even faster, and or the dirty flag, which is needed for HSM. We must also have a guarantee in that case that we cannot change stripe objects without the knowledge of the MDS. Now, if the MDS evicts a client, but the client isn't evicted from the OSTs, that's possible. So there's another reason for why we'd like to have some sort of a global concept of client connectivity. So we all know about Moore's law and the fact that it's breathing down our necks the whole time, that machines are getting bigger and bigger, and for heading towards exascale, we're talking about millions of nodes, thousands of server nodes. We're already, in the Fujitsu presentation, we already saw vast numbers of server nodes. And in that case, prompt fault handling is going to be mandatory. We're used to MTTFs at the moment of hundreds of hours. That could come down to hundreds of minutes. If it's going to take you many tens of minutes to recover from a fault, your utilization is going to go through the floor. And so prompt fault handling is going to become totally mandatory so that we can avoid problems, continue in production even though a server is in trouble, even though clients are holding resources when they crashed, and so that we can complete recovery quickly. So here are some requirements for a health network. We need low latency fault detection. And we need that for servers and clients. And it needs to be reliable. It can't be giving false positives. At least not very much. We can cope with some low level. We need low latency global notification so that when a fault event is detected somewhere, the rest of the cluster is notified scalably and quickly. If we're going to have some sort of network like this that is capable of global intelligence, then we should exploit it for for server collectives, so that we can more closely couple state and share it across a bunch of servers. So, for example, a scalable way of doing quality of service. If we can start gang scheduling our servers to give particular jobs, particular levels of resource, we can overcome the issue of the user who is totally swamping the MDS while the file per process create job is going on. And the visualization, to stop the visualization jittering while the massive checksum is going on. It has to be scalable. It has to cope with millions of clients, thousands of servers. It should be relatively simple to administer. You've all probably battled at some point with failover configuration. If it's going to be, that's just pairs of nodes at a time. We can't afford for this to be hard to set up. And obviously it has to have low overhead, both on server CPU and on networking, because the main object of the exercise is to do I/O, not send pings around. So I think there's some valid assumptions we can make in the design of a health network. We should assume that servers and LNET routers are not malicious, that they participate constructively in health network protocols, but they may be buggy. So we have to be somewhat defensive in the case the peers run across a bug which causes them, for example, to start up and crash and start up and crash. We should assume that all the servers might crash together or be powered off together. I mean, whole machine power-offs have to be anticipated. But normally, we should assume that servers are up stably for at least tens of minutes at a time. So in other words, we don't have to cope with a completely dynamic population of servers. I don't think we can rely upon that for clients. Clients could be in any state. Clients could be rebooting constantly, and the health network must be able to make progress while that's going on. I think something else we have to accept, given Lustre's fundamental architecture, clients need to connect to every server, and therefore there is an unavoidable order n overhead on initial client connection. So we have n clients, they all have to connect to the system somehow, and so why don't we just take it on the chin that there's going to be an order n cost for doing that. So I think the first thing we have to work on is Elmet. We need an uncongested, highly available, low latency network. And in every Lustre installation, there's one there. It's the network that's used for normal communications. But what makes it hard to use for health network communications is the fact that it can become congested by normal in-band communications. Now, there's already a facility within Elmet, inside the LNDs, to exchange messages even though upper levels are totally congested, because we have to be able to set up our RDMA at any time. And so that facility could be extended in order to implement high priority messages. So we have reserved resources in all the Elnet drivers that allow you to do these sorts of setups. We can guarantee that the health network will be an eager reader and therefore will free any network resources in a timely fashion. And therefore we could implement a high priority Elnet that's private to the health network. We don't want to use routing on this network because we don't want to become confused by Elnet router failure. And we also want to do some sort of rate limit, because this health network, if it becomes congested, stops being useful. So by rate limiting the ingest, we can guarantee that there's enough headroom to bound message latency. The other thing we need to change in Elnet is make peer death detection more prompt. What that means is it mustn't confuse router congestion with peer death. And I think that's fairly straightforward. We have to ensure that even though messages are not normal messages are not able to progress through the network, that peers still keep each other informed that they're healthy. So in other words, when we find that that the message queue to a particular peer is no longer moving, we can exchange relatively low frequency health pings at a very low level. This only needs to occur when there's active messaging. Now, there is one requirement on the underlying physical network. It mustn't have any beer timeouts. Some of you may be familiar with that term. Galen. Indeed.
Is it just you need to bound that time
The-
to some
So,
quote-unquote reasonable value?
yes, so unless people heard here, what Galen was just saying, that networks all have fundamental timeouts. What's the big deal with a beer timeout? Well, the big deal is that it's long, because this low-level timeout, the minimum, if you like, well, actually, it's the maximum latency of a normal communication on the underlying network. Everything else is going to scale to that, because if that timeout is long, we have to allow for it. It means that it can be expected that communications could be relatively high latency, and therefore the timeout. Am I about to time out? And therefore the timeout could be long. So really, the reason I say no beer timeouts here is that fundamentally that timeout drives everything else. And so the shorter it is, the more promptly we can do global health detection promptly. Now, that might mean that you might want a separate LNET reserved entirely for health communications. If that is the only way you can guarantee that the low-level physical network timeout is going to be short enough. So, the concept here of the health network is that we create some sort of a spanning tree over servers and LNET routers, basically the trustworthy nodes. All of the non-trustworthy nodes, the clients, they should be hung off the trustworthy nodes and distributed over them, so that the trustworthy nodes are sharing the load of monitoring the untrustworthy loads. And what I think of here is a network in which you have a very highly available route, and I'm assuming something like Paxos would guarantee that, and that it would have quite a wide branching ratio. It's going to be on the order of the forwarding latency times the send rate. So parent node selection would occur in the root node. The root would maintain the tree topology, and as nodes join the network, they'd be assigned a position in the tree by the root node. So for client nodes in the same LNET network as the root node, they would go directly to the root nodes. For nodes in other LNETs, they would have to pick one of the routers, which would then proxy for the root. So in this model, we're communicating on a tree always. All communications converge towards the root, and then the result of a communication is disseminated back down the tree again. As communications requests converge towards the root, then they are combined. That's what makes this network scalable. Now, there's some sort of rate limiting going on here, both to avoid congestion and also to maximize the chances of combining so that we have more scalable communications. The concept is that while the topology of the spanning tree remains the same, we have a version number, we have an epoch, if you like, for that instance, for that lifetime of the collection of servers. And we expect to be able to do collective communications, or many hundreds, within a single topology change. So as requests converge towards the root, at the root, the notification is then turned around and sent and either steered back down the tree again towards the originator, or in the case of broadcasts, duplicated back down the tree again. This gives you a scalable way of doing global notifications. It also lets you do collectives if the requests, as they converge towards the root, block for all of their peers. So this tree will then use normal communications across the tree to detect pure liveness, and have a protocol for rejoining the tree and issuing notifications. Basically, you have to rejoin quickly, and then when a notification reaches the root, it's basically notification of the death of part of the tree reaches the root. It's basically racing with the clients there, with the nodes that left the tree. It's racing for them to rejoin the tree. So if a failure notification arrives at the root and the nodes that were below a dead node failed to reconnect, then at that point you can issue a global notification that those nodes are no longer present. So I'm just going to have to skip quickly through the benefits of this. Basically, it gives you scalable server collectives so that you can share information, you can share state across a whole set of servers. It gives you reliable server restart notifications so that we can shrink the recovery window. And we don't have to back off to timeout-based recovery in the absence of a particular crucial resource, like the MGS, for example. It also gives us the opportunity to do scalable global client connection and eviction by using the fact that clients join the health network. Effectively, at that point, they've connected to all of the servers, because we can use the health network to broadcast the fact that this client has connected everywhere. So we have a global connection and disconnection concept. And that means we can now implement some interesting features that really enable much better performance reliably and safely. Thank you. Any questions? Preferably from the back of the room.
We're tight on time. Wow. Thanks.
So I'll be quick and just have a comment. I just wanted to say, when you describe the ping, the Elnet pinger problem, it tends to be a little worse. Your diagram showed clients sending out pings at whatever rate that they were doing, but we tend to see that those are synchronized. Clients tend to mount file systems at the same time, and the pinger interval starts at that time. So you get floods of pings all at once. Bugzilla 12471, it's an old bug. It describes the problem, if you're interested.
Yeah, I think we should do a short-term fix for that.
Anybody else? All right. Oh, Galen Shipman.
So I mean, this has a lot of commonality with other requirements, for not just for exascale, but for systems that we're looking at in 2015. Have you looked at any of the work done in like CIFS or the fault-tolerant backplane work out of Berkeley and others?
So no, but I would just love to get a bunch of interns working on prototypes here, because I think...
Because, this is the type of thing we could evaluate different approaches at scale.
So the devil here is in the detail, and you really have to prove out these ideas. I think a big issue is going to be sort of false positives and pathological situations. What happens when a whole rack powers off? Are we really resolving the race between pronouncing a whole subtree dead versus that subtree struggling to reconnect somehow? What is a health network, because it's doing collective communications like this, is not exercising all the paths between servers and clients. And so we still need to handle the cases where point failures asymmetrically affect different parts of the machine. So yeah, there's lots and lots of detail to be worked through.
Okay, if there are further questions, be sure to pester Eric after the break. Or during the break. Yeah, that's right. Let's go drink some coffee. Thank you, Eric.